everyone, and welcome to Adaptive Thresholding Lecture. My name is Olivier Rukundo. I am a researcher at the University of Eastern Finland. Today I want to talk about the local or adaptive thresholding technique, and after that I will show and comment on examples of segmented medical images. Going back to this previous lecture image example, applying a single threshold couldn't give good segmentation result over this image. For example, see the result obtained using the threshold equal to 127, and also see the result obtained using the threshold equal to 89. So here, for example, these segmentation-based outlines are not good for the representation of adenovirus because other areas that do not represent adenovirus are also outlined. In brief, when the background is not constant or when the background illumination is uneven and the contrast of object varies across the image, thresholding may fail, or it may work well in one part of the image and fail in the other. Solutions such as preprocessing an image with a unimodal histogram could attempt to make thresholding work well. As can be seen here, some of preprocessing or gray level correction techniques were used to make a single threshold work. In the book titled Digital Image Processing Using MATLAB, the preprocessing process is equivalent to thresholding f of x, y with a locally varying threshold function t of x, y. Here it's important to note that the local thresholding or adaptive thresholding is generally based on splitting the image into overlapping sub-images and calculating thresholds for each sub-image, or else examining the intensities in the neighborhood of each pixel. Now, let's see this example. Here we have an example of input image, which, as can be seen, is not class double. Therefore, we must convert it to the equivalent image of class double by rescaling or offsetting the input image values to the interval from 0 to 1 as shown here. So this is the resulting matrix. Now, to calculate the local threshold value at each pixel, we first pad this image by replicating these values. And in this way, we can add another layer here, and then we form a padded image. And next, we use the mean or median or Gaussian weighted mean options. Then we have to consider the neighborhood size. For example, let's say the neighborhood of 3 by 3. In this case, we are going to consider these values and then apply the mean. So each of these options must consider the neighborhood size to compute local statistic around this pixel, this one. So the neighborhood size is computed around each pixel, each of all these pixels, all of them. In this example, we use the mean, and here is the resulting matrix T of x, y. And this has the same size as f of x, y with normalized intensity values, first all kept in the range 0 to 1. Now, the next step is to convert f of x, y to a binary image using T of x, y. And here is the resulting G of x, y matrix. Now, for example, let's look at this value here from f of x, y, and this value here from T of x, y. If you look at this situation here, we can see that this 0.1 is less than 0.14. 0. Therefore, the output will be 0. Let's look at another example. For example, this value here. And then we look at this one here. We can see that 0.98 so is greater than 0.86. Therefore, the output will be 1. And that's why here we have 1. So this is what happens with local or adaptive thresholding technique. Now let's look at real images segmented using this segmentation technique. Here I used the MATLAB built-in function adapt thread with different statistic and sensitivity factor parameters. Others are set to default. Here I would like to add that sensitivity is a scalar in the range from 0 to 1, and it indicates sensitivity towards thresholding more pixels as foreground. And in that adapt thresh function, statistic is used to compute the local threshold by mean, which is the default in that function, or median or Gaussian. And also I used the MATLAB built-in function InBinarize to convert an intensity image to a binary image. Now let's use this image example. And here we have the mean, and here the sensitivity is equal to 0.6, and here the sensitivity is equal to 0.4. And here we use the median, and the sensitivity here is 0.6, and here it is 0.4. And here we use the Gaussian, and the sensitivity is 0.6, and here the sensitivity is 0.4. Now let's use another image. Here, this is the column of the mean, and here the sensitivity is equal to 0.6, and here it is equal to 0.4. So you can see the difference between the result at different when different sensitivity values were used. And here we use the median to compute the local statistic, and the sensitivity is equal to 0.6, and here it is equal to 0.4. So these are the results obtained. And here we use the Gaussian. Here this is the case of 0.6, and here this is the case of 0.4 sensitivity. And let's use another image example. Here we have, in this case, here at 0.6 and with the sensitivity equal to 0.4, this is the result obtained. And in the median column, here we have 0.6, and here we have 0.4 sensitivity. And in the Gaussian case, here we have 0.6. Let's look at another image example. So here we have this column of mean with the sensitivity equal to 0.6, and here with the sensitivity equal to 0.4, and in this second column of median we have the image produced using the sensitivity equal to 0.6, and the image produced all displayed using the sensitivity that is equal to 0.4. So this is how it looks like. And in this case of Gaussian, and this is the image that corresponds to 0.6, and this is the image that corresponds to 0.4. Now let's look at the final image. For example, this one. So this is what we get. And here, this is the case involving 0.6 sensitivity, and this is the one involves 0.4. And here, with the median and sensitivity that is equal to 0.6. So this is the image that we get. This is the kind of outline we get. And these outlines are based on segmentation outcome. And this is the case of sensitivity that is equal to 0.4. And finally, this Gaussian column. Here we have the image corresponding to the sensitivity that is equal to 0.6, and it is one, and this one corresponds to 0.4. And here the adenovirus is outlined correctly, but other parts are outlined as shown here. And here, in this case also, adenovirus is outlined correctly, and other parts are outlined as shown here. More details on this technique or many other image processing and analysis techniques can be found in the books such as Handbook of Medical Image Processing and Analysis or Digital Image Processing using MATLAB. Now, this is the end of this lecture. Thank you.